Hello everyone, my name is Paweł Nowakowski. Today we will discuss sample preparation techniques for scanning electron microscopy characterizations and failure analysis of advanced semiconductor devices.
Today's speaker, Dr. Paweł Nowakowski, is a senior scientist at Fischione Instruments, where he has been contributing his expertise since 2015. He holds a PhD in materials science and engineering from the University of Toulon, France, which he completed in 2008. After earning his PhD, Dr. Nowakowski worked as a scientific member at Nantes University, France, where he focused on nickel-based superalloys. In 2010, he joined Oxford Instruments as an EBSD expert, further deepening his expertise in electron backscatter diffraction techniques. Over the past 20+ years, he has developed a wealth of knowledge and experience in the field. His areas of specialization include the layering techniques and instrumentation development, broad ion beam instrumentation development and sample preparation, focused ion beam sample preparation, electron backscatter diffraction EBSD techniques, and material deformation and failure analysis. In 2022, Dr. Nowakowski received the Best Paper Award at the ISFA conference. He has also been an invited speaker at both the ISTFA FIB user group and the sample preparation user group. Since 2025, he has served as a co-chair of the ISTFA sample preparation user group. To date, he has authored over 60 peer-reviewed publications and delivered more than 55 presentations at international conferences.
Here is the outline for today's presentation. We'll start with objectives, then we'll move to the introduction to the sample preparation techniques. We'll talk about damage induced during sample preparation. Then I will show examples of different sample preparation and I will finish by summary. The main objective of this presentation is to guide you on how to select the appropriate sample preparation method for advanced semiconductor devices analysis using SEM. Let's begin with an introduction to sample preparation. Here we see a typical microelectronic device failure analysis workflow. It starts with fault isolation through electrical measurements, followed by decapsulation and fault identification using SEM-based technique like EDS, EBSD, or other analytical methods. It's important to understand that for effective failure analysis, the sample needs to be carefully extracted from the device and adapted to meet the specific requirements of the microscopy and analytical techniques you will be using. There are various sample preparation techniques used in failure analysis, each with its advantages. Here I will list some of the most commonly used methods in failure analysis lab, including mechanical polishing, focused ion beam, broad ion beam milling, chemical etching, and plasma etching. These techniques enable the preparation of cross-section planar samples and the delayering of semiconductor devices. Often, a combination of those methods is used to achieve the best results. For sample preparation to be successful, it is critical that it does not alter the device's microstructure or chemical composition. The process should not induce any deformation, cracking, or delamination. In other words, a good sample preparation should be artifact-free and the prepared sample must accurately reflect the key characteristics of material under study. Now, let's discuss some of the potential damage that can occur during sample preparation. Here we have some example of 3D NAND memory device that was mechanically polished using 0.5 micron diamond paste. As you can see, there are a lot of scratches and surface damage. It's important to remember that the depth of the damage can be up to 3 times the abrasive grit used in the final polishing step. For instance, if 1 micron diamond paste is used, the damage depth could exceed 3 microns. This damage results from accumulation of scratches and dislocation in the material. Ion milling, especially using FIB, can also induce damage to the sample. Here we have an example showing damage caused by gallium FIB. Gallium ions can penetrate the material to depth up to several hundreds nanometers, depending on the material and ion energy. These slides compares austenitic steel sample prepared by argon broad ion beam milling without any structural damage and the same sample exposed to varying FIB ion energy. As you can see here, even at low ion energies, significant structural damage is visible. The FIB milling process induces enough atomic displacement and vacancy to cause dynamic strain phase transformation of austenite to martensite. This highlights the need to be cautious when using ions for sample preparation, particularly when using FIB ion beam milling. Another issue during the ion milling is a thermal structural damage. Here we have a sample of low melting point thin bismuth alloy solder. Even with 1 kV energy, we can see thermal damage caused by the heat generated during the ion milling process. This results in incoherence between the bismuth and tin phases. To address this, cryogenic stages were developed for FIB and broad ion beam systems to handle thermally sensitive materials. As you can see in the second example, using higher energy with a cryostage minimize the heat effect and no observed damage is found on the sample. Now let's move to the sample application examples, starting with cross-section sample preparation. FIB is a powerful tool that provides high-quality, site-specific results quickly. However, it has limitations: small sample areas, curtaining effects, and damage as previously discussed. Broad ion beam milling with protective mask allows larger cross-section up to 7 mm. The mask protects the sample edge, minimize damage compared to FIB due to the use of lower ion energies and different ion species. This is an example of cross-section preparation using broad ion beam milling on solder bombs and microelectronic packages. First, the affected bomb is identified electrically, then the sample is masked and material above the mask is removed to create a large cross-section. Here's a cross-section of 12 solder bombs where delamination in the copper pad area is identified as a failure. You can also cut and embed the device in resin using mechanical polishing or a combination with broad ion beam milling. Mechanical polishing is a complex and very user-dependent process requiring extensive cleaning, and colloidal silica is difficult to remove, leading to long polishing and cleaning times. So EBSD results show that with mechanical polishing, the interface between the copper pad and solder is obscured by shadowing from the copper pad due to differential material removal. Contamination and corrosion from packaging and mechanical polishing slurries also make observation difficult. However, argon ion milling preserves the interface and ensures a clean surface, making failure analysis easier. Here are some key tips for achieving accurate cross-section preparation. So first, minimize mechanical grinding and polishing, limit contact with water or aggressive solvents, use broad ion beam milling as a final polishing step. Next, let's move on to silicon backside tinning. Here's an example of device ion milled using 6 kiloelectronvolts from the backside. The sample was initially mechanically polished down to 100 microns, followed by future polishing with broad ion beam milling to reduce the thickness to below 1 micron as shown in the fib cross-section across of the area interest. Thickness of silicon was continuously monitored using an optical camera during ion milling. Here are some tips for accurate silicon backside tinning. Mechanically polish the silicon down to 10 microns. Use chemical etching with hydrofluoric acid to reach 1 micron thickness. Achieve the desired final silicon thickness with broad ion beam or fib milling. Next, let's discuss device delayering. When selecting the layering technique, two key parameters must be considered: the required area of interest and the level of uniformity. The most common method used today are based on ion milling, which include focus ion beam, broad ion beam milling, and new large-scale area automated delayering technique. So fib provides a very uniform but relatively small area. Broad ion milling can cover a large area up to 3 mm, as you can see here, but uniformity may not be perfect. The new delayering technique can cover area up to 10 mm with excellent uniformity. We will cover all three methods in this presentation. Now let's talk about the challenges of delayering using ions. The key parameter is the starting surface flatness. A flat surface significantly improves the results of large area delayering by ions. Additionally, these layers should be removed using chemical etching or mechanical polishing, or a combination of both methods yield the best results. The plasma fib is an extremely precise delayering system. Differential material removal is minimized by using a specific gas mixture during the process. Material removal can be controlled through direct observation or by measuring the absorbed beam current. User interaction is required. In the case of broad ion beam milling, up to 3 ion beams can be used depending on the instrument. The beams are aligned to uniformly cover the desired area, and differential material removal is minimized by using a low milling angle. Edge pointing can be achieved using an integrated digital camera interferometer or by cycling between the ion milling system and the SEM. User interaction is essential. Depending on the system used, uniformity of up to 200 nanometers can be achieved over a 3 mm diameter area, as shown here by fib cuts of a layer 3D vertical memory devices. For large-scale area more than 3 mm in diameter and high uniformity, at the tens of nanometers level, a different technique is required. This new delayering method uses a large, uniform 0.5 mm argon ion beam, as you can see here. The beam can scan area of up to 10 mm in diameter with surface flatness controlled through feedback from integrated analytical detectors including backscatter electron imaging and EDS measurements. The entire process is automated and performed in a SEM environment requiring no user interaction. The instrument operates in a sequence of looped operation. First, data is acquired to determine the top layer and surface flatness. Milling parameters are then adjusted as needed, and material removal occurs through ion milling. All of this happens automatically in the background with no user interaction. The next slide shows an example of a layer being removed. After 3 sequences of ion milling, the top M2 layer was completely removed, exposing the via layer underneath. The goal of the delayering process was to remove metal layer 2 while having only a small portion of vias on the top of the material metal layer 1. Let's see how we did. As you can see, we obtain a very clean, large and uniform area across region of interest. STEM images show that the vias protrude about 20 nanometers above M1. We successfully achieved surface flatness within 50 nanometers over an 8 mm area. With this example, I will conclude the presentation and move to the summary. So please remember that effective sample preparation requires careful selection of techniques to avoid artifacts, minimize damage, and preserve material integrity. Mechanical polishing, fib, broad ion beam milling, and other methods each have strengths and limitations. Often a combination of those techniques yield the best outcome. Each sample preparation technique must be carefully optimized to achieve the optimal results. And the new automated delayering technique provides high uniformity over large areas, improving efficiency and accuracy in semiconductor failure analysis. Thank you very much for your attention.